All right, good morning, everybody, or I guess whatever time it is. Here it's a beautiful fall morning in Colorado, so let's do some physics. We're going to do electrostatics. Electrostatics is an interesting and somewhat confusing world. So we're going to start out by just going through the terms. See if you can fill this chart in on your own. Okay, let's see how we did. Charge. We got that variable. Measured in coulombs. Okay, sometimes we might run into microcoulombs, which to convert back to coulombs, we just tack on a times 10 to the negative 6. Also important to know, let's put this on here, charge of an electron is equal to negative 1.6 times 10 to the negative 19th coulombs. And a proton, we of course just make that positive. This is a scalar quantity. Electric field, the variable is capital E, and it is measured in newtons per coulomb. It is a vector. Okay, now at this point, these things all start to sound alike, and that's one of the reasons why this unit is semi-confusing. We really have to know the difference between all of these different things, what they're measured in, and their variables. So we'll work on that a little bit today. Okay, so electric force is just F, like any force, but we put a capital E down there to tell us what type of force. A force is a force is a force, of course. Nobody's laughing. Well, that means that it's measured in newtons, and it is a vector. Electric potential. Okay, electrical potential is like it's kind of like a gangster with a lot of alias names. So, electric potential, aka potential difference, aka EMF. Also known as voltage. Okay, all of these things are electric potential. So EMF, voltage, potential difference. Okay, we kind of use these terms for different situations, but they are all just voltage. Okay, delta V. Up here we had newtons per coulomb. Down here, joules per coulomb. It's the energy per unit charge. It's how much energy is behind that charge. And more commonly, volts, abbreviated capital V. And this is a scalar. Okay, it has magnitude but not a direction. Okay, electric potential energy is capital U, which we use for any type of potential, but we put a capital E down here to tell us that it's the electric potential energy, is measured in joules, and is a scalar. Okay, so those are our basic terms that we need to talk intelligently, speak intelligently about these things. Next, let's go over the equations that we need to know and how, in the situations they are used in. I'm going to break the equations up into two parts here. We have equations that are just for point charges, and then we have equations where we are working with parallel plates. Okay, so our point charge equations, let's go over force first. The force between 2 point charges is given by Coulomb's law. That's Coulomb's law right there. I think they even teach it in AP Chem nowadays. simply put, if we have two charges here and we have the distance between them, that gives us the newtons. Okay? Now, a similar looking equation is electric field. Okay? To get from this to electric field, all you do is drop one of the charges. And I'm going to actually use a capital Q here. Okay, and here's where we use this. We use this if we've got one charge over here and we want to know the field at a certain point around that. Okay, and we don't have a force here. We just have one charge out in space. We want the field at some distance. Okay, and we'll go into more on this. This right here, very important to remember. It is the charge creating the field. Okay, and this, by the way, is not on your equations page. It can be derived very easily from stuff on your equations page, but it's not on there. You have to know how to get it. And I just remember, oh, drop a charge from the force equation, and you've got the E field equation. Okay, the potential due to a charge out here in space is K Q over R. So same as this, we just drop a squared, and that is actually on your equations page. I'll show you where to find all this in just a second. And finally, potential energy between 2-point charges. Whoops. I'm just going to go ahead and start that over. K, Q, 1, Q2 over R. Okay? So that's the same as the Coulomb's law, but no squared. Alright, now let's look at these on our equations page over here. Here's Coulomb's law. Alright, they put a bunch of absolute values and nonsense in there that I don't really worry about too much. We'll talk more about the force direction later and why that's in there. They also put this constant, which is a huge pain and nobody uses it that I've seen ever. So I don't know why they don't change that to K. I think they want to make it a little bit more confusing for us, unfortunately. So we've got that. And oh, look at this. Okay, they did add the E field equation for us. This used to not be on there. So KQ over R squared, and then here's the voltage equation, and that's where we're going to find our stuff. Okay, now some things that are used for both sets. Well, let's go over parallel plates first. There's one equation on here that is specific, that we only use for parallel plate situations, and it's the E field equation. Delta V over delta R. Okay. Now, sometimes you'll see it like this, delta V over D. I'll write it like that on the board sometimes. This is the plate separation. And if we know it, and we know the difference in the voltage between the two plates, we can get the E field. Okay? Now, here's some parallel plates. Here's the distance, or R, we could call it. If this is at plus 30 volts, and this one's at negative 30 volts, what we would do is we take the difference between those. So the difference is going to be 60 that we're going to use. So we need to always make sure we're using the difference in the voltage. Delta V equals 60 volts. Okay. All right, and that would get us the E field again. Okay, now equations we use for both. The definition of E field is a force per unit charge. Okay, and if we go back to this, let's look at that. Oh look, a force per unit charge. Okay, newtons per coulomb. That's the definition of E field. We like to use this rearranged a lot as QE. Okay, so be aware of that. Another thing we use for both situations is potential is QV. Okay, and delta U equals Q delta V. Alright, so this is on our equations page as well. It's right there. Okay, and we'll talk about how to use that here later in the video. Okay, so here's the three that I just added, that one, and this one here. Okay, now this is one thing that drives me crazy as a physics teacher. People misuse these equations all the time. Okay, you may only use them for point charges. Alright, so we know the equations and our variables now. Let's talk about this. We're going to compare gravity to point charges. This is a huge standard on the AP test. There's a bunch of learning objectives that say that we have to know how to compare and contrast these things. Okay, so we're going to take it back to the good old days. And we're going to go back to Physics 1 and we're going to review gravity a little bit. And then we will relate it to the new stuff, point charges. Okay, so remember way back when we learned about planets and satellites and the force of gravity and little g, all of that stuff. Okay, let's say we've got a big, massive planet here. Okay, and we want to talk about the gravitational field around this object. We usually talk about the little g value at different places. Okay, now we can get the little g value by doing this simple little proof. Okay, the force, if I have some object out in space, the force on that object is its mass times the little g at that point. But we can also get that force by using universal gravitation constant. Okay, so remember this equation. And what happens is the mass of the object actually cancels. Okay, so what that means is, let's say we have point P out here in space, just some point away from this big mass. The little g value at that point can be given by this equation. Okay, now there is no mass at this point. Okay, that's the most common mistake with this equation, is people try and talk about the mass at that point. The mass of this big object is what we care about, and the distance between these two is our r value. Okay, and we can get little g. Now at the surface of Earth, okay, if this is Earth and we're right here, that value is 9.81. Okay, and the sun's got a little g value, Jupiter's got a little g value, the moon's got a little g value of 1.6. Okay, and those values are all at the surface, but we could also get the acceleration due to gravity right here. Okay, this describes the gravitational field at this point. Alright, now let's say we've got another point out here, we'll call it point X, okay, and we put a spaceship here. Okay, we're going to put something out there this time. Now that we've put a mass at this point, we have a force. So we can say the force of gravity is equal to big G times the mass of the planet times the mass of the spaceship, we'll put little m right there, over r squared. Okay, so we don't have a force until we actually put a mass at that point. All right, that's what you learned probably last year about gravity. Okay, now we can use this to talk about point charges. Okay, so instead of a big mass out in space, let's put a big charge out in space. Let's call it Q. All right, and we'll make it positive. We'll call it plus Q. And let's put a point P out here and talk about the field strength from this at this point. Okay, if we're going to do that, we are going to talk about the electric field value. All right, and we can look this up on our equations page. It is K Q over R squared. Okay, now a couple of things. Note that we don't have a charge here. Okay, this is just a point, an empty spot in space. All right, and this field is being caused by this big charge over here. Okay, now let's have another point over here. Call it point X. And we will put a little negative Q right there. Okay, on that point. Something's charged up right there. We now have a force. Okay, and we're going to say that force is equal to K Q Q over R squared. Okay, now what kind of force is this going to be, attractive or repulsive? We always get that by just looking at the diagram. Okay, and that's why the equations page has absolute values around all this, because the sign of this force doesn't actually tell us much. Excuse me, we need to look at our diagram to tell if it's attractive or repulsive. Okay, so two different charges, it's going to be an attractive force. If these are both negative, it's going to be a repulsive force. So it doesn't actually tell us the direction the sign of this wouldn't, it just tells us attractive or repulsive. Okay, now notice that these equations look very similar and these equations look very similar. Okay, so they both have constants. All right, now the big G constant is a very small number. Okay, so let's get out our equations page for a second. Okay, and this one has wax spilled on it. Sorry. Okay, this one's to the negative 11th, and K value is to the 9th. Okay, gravity is said to be a weaker force than electrostatic force for that reason. Okay, they both have constants. They're also both inverse square laws. So you can see that the inverse of the square of the radius matters in both situations. One thing that is different about the two, however, is this force can be attractive or repulsive. This force can only be attractive. You don't have two masses that repel each other. They only attract. Okay? Whereas over here, you can have either situation. Okay, so hopefully that clears some things up and relates the two for you. Let's work on field lines a little bit. We have to be able to both draw electric field lines and analyze a diagram that's given to us on field lines. Okay, so let's do the most basic one first. Let's say we have just a single point charge out in space, and let's say it's positive. Okay, take a second and try and draw the field lines around that. Okay, should have drawn something like this. we're going to draw symmetrical arrows going apart, okay, going away from the positive charge. Okay, now if I had a stronger charge here and I wanted to compare two situations, I would just draw more lines. The more dense the lines are, the stronger the charge creating those lines is. Okay, so that'd be for a negative charge. Or, sorry, positive charge. Okay, so over here for a negative charge, we are going to draw field lines like this. Going to draw them symmetrical, and we are going to draw them towards the negative charge. These are our two most basic field line diagrams. Okay, now here's what I teach my students. We'll put it down here. WWPCD. Lots of exclamation points. Okay, that stands for what would positive charge do? Okay, so let's say I put a positive charge right here, a little positive plus Q test charge. Okay, wouldn't it have a force on it in this direction? Wouldn't it go towards the negative? Yes, it would. Let's say I put a little plus Q right here. It's always for a positive charge. It's going to have a little E field vector in that direction. It's going to experience a force in that direction. Okay, now just because there's field lines does not mean there's a force. There's not a force until we put a charge there. We talked about that up here on the top of the page. Okay, what would positive charge do? Remember that little saying, and it might help you out. Okay, all right, now let me give you a couple more situations and you can pause the video and try and draw the field lines. What if we've got positive and a negative like so? We'll try that one. Or two positives. Try and draw that one. And probably one of the most important of all of them, good old parallel plates. Okay, and for this one, let's draw positives on the top plate and negatives on the bottom plate. Okay, work those on your own. Let's see how we did. Okay, so I like to draw the easy lines first. How about just that? Okay, what would positive charge do? It's going to want to go away from that and towards that. Okay, and then what ends up happening is we get these curved lines. Don't forget to put arrows on the end of your field lines. Okay, a lot of people will just draw a line like that, and that will get you less points on an AP problem. We have to show where those lines start and where they end. Okay. Alright, then, so we're going to keep getting these curved lines like that, and then we're going to start getting curved lines like this. Oh, let's draw some more easy ones too. Let's draw that, and let's draw that. Okay, something like this. Alright, then on the other side, we're going to have lines curving in. And it's going to look something like that. Okay, and we could draw more and more and more. Alright, we'll leave it like that. Okay, now these, let's draw the easy lines first. I'm going to have one of those. I'm going to have one of those. I'm going to actually have zero field. I even saw a test question one time where the students got points for not having anything in here. because the field is going to be 0 in the center. There's not going to be a line going through there. Okay, then we're going to have these kind of asymptote looking lines coming out like this and down. Okay, and your drawing should look something like that. Okay, and you can look these two up online and see how my pictures match up. They're pretty good, but if you want to see how to draw these a little bit with a little bit more perfection, you can check that out. Just Google it. It'll pop right up. Field line diagrams, field line drawings, whatever. Okay, now parallel plates. These need to be parallel. Your field lines do, and they need to be coming from the positive to the negative plate. They need to have 90-degree angles here. And then around the edges, we call them edge effects. You'll actually get these curved lines. But we mostly care about the lines in between. Okay, now this also has a lot of alias names. Okay, so we call them parallel plates. We call this a capacitor, or a parallel plate capacitor. We call this a uniform field. Okay, these are not uniform fields. All right, these are also not uniform fields. These have straight field lines, but those field lines are not parallel. I've got less field line density here than I do right here. Therefore, it's not a uniform field. Okay? This is the only uniform field. You have both parallel, okay? Lines have to be parallel. And they also have to be straight. Okay, that'll give you a uniform field. The field density is the same everywhere. All right, this is a huge deal. Comes up all the time on AP problems. All right, so we can draw those now. What would positive charge do is the main thing. Okay, now what if you are asked to draw equipotentials? Okay. I love G2 pens. Look at this. This is the best pen ever made. Okay, I'm going to use my pink G2 to draw the equipotentials on a few of these diagrams. Equipotentials are always parallel to field lines. Always, always, always. And you might have even done a cool lab where you did equipotentials on the Excel spreadsheet and stuff like that. Okay, kind of a fun lab. So these are equipotentials right here. They are places where the potential is or equal potential lines. They're also called iso lines. That's another alias used to confuse us. Iso lines. Okay, isolated potential. All right, is kind of what that means. Okay, so these are always, oh my gosh, I am so sorry. I am so sorry. Perpendicular to field lines. That's a big mistake. Okay, and I don't have students here to catch my mistakes like I usually do. Okay, so here, these are all perpendicular to our field lines. All right, and yeah, that's basically what we need to know. These points are all at the same voltage. Okay, along this line, same voltage everywhere, same potential. Okay, now for these, our equipotentials look like this. Okay, this is a 90-degree angle. This is a 90-degree angle. This is a 90-degree angle. Okay, and all the way around. If you've ever looked at a topographical map, topo maps show equipotential lines of gravity. Okay, so this might be a peak on a map, a mountain. In Colorado we have 14,000 foot mountains. Okay, this might be 14,000 feet. This might be 13,800 feet. Okay, and so on down the mountain. Okay, here same thing but with voltages. Okay, this might be plus 30 volts. This might be plus 20, plus 10. Okay, going down, and we would calculate that using actually our voltage equation, which is this. Okay, we have a radius, a charge, and we could figure out from this point charge different voltages at different points, different potentials. Okay, the negatives would look different, but we like to think of the negatives, if we're thinking three-dimensionally, as a well. Okay, and we're looking down into the well and our lines are coming out like that. Okay, now the equipotential lines for these are a little bit more complicated. We don't usually have to draw those, but if we did, perpendicular. Okay, every equipotential is perpendicular to the field lines. Make sure you fix that on this. Okay, guess what? It is time for, you know it, Name That 90s Song. One of my favorites. Okay, what do you got? Artist and song name. Oh, such a good one. Maybe write it down there. Let's work a couple problems that have to deal with E fields and also Coulomb's law. Here's a ranking task. Try this one and then try this little puzzle down here. This one's a little bit different from some of the stuff we've done. You have students arguing about physics. Look at that. It's the weekend and they're hanging out, and Alfredo, Brian, and Carmen are like, let's talk about physics, right? That would happen. And you have to decide which of them is right. This is a very common AP question type. Okay, so let's pause, work this whole page, then unpause it, and I'll show you how to do it. Okay. A reminder, if I tell you to pause, please do it. If you just copy down what I do right here, you really are learning nothing, and there's no point in watching this video if you don't do these on your own. Okay, so this is a ranking task, and they would like us to rank the acceleration. Okay, greatest acceleration and least amount of acceleration, or we have these choices. Okay. It's the same, it can't be determined. Okay, so those are choices as well. Alright, now these are point charges. Coulomb's law for force does apply here. And what's going on here is there's only one force acting on each of these particles, and that's electrical force. So we can say that Fe is equal to the F net, since there's only one force. Now the Fe is going to be given by K, Q, Q over R squared, and F net we can say is Ma. Alright, now we do have masses and charges to deal with here. Okay, we want to find the acceleration, so I'm going to rearrange this and say acceleration is going to be equal to KQQ over R squared times the mass. Alright, now the radius for all of these situations is the same. Okay, the charges aren't the same, the K value is also the same, so I'm going to say that acceleration is proportional to and I'm going to take that out, and I'm going to take that out because it's the same for everything. So I don't really need those in my comparison. Acceleration is proportional to the charges multiplied and the mass. This is the stuff that actually matters for our acceleration. Okay? So let's take a look at that. If we multiply the charges and divide by the mass for each one, we will get a ratio that can help us to decide the ranking. Okay, so here I have a 1 times a 4, so I'm just going to do some quick math for each. 1 times a 4, all right, divided by a mass of, I'm just going to call that a mass of 1. Okay, so that's kind of my acceleration ratio that'll help me decide for A how to compare. Okay, for B, I also have a 4 times a 1 times a mass of 1, so I get that for my acceleration. Now I'm not actually plugging in numbers, okay? I'm just doing some ratios here to help me decide. Let's draw an FBD on these just for fun to show us what's going on. The force here is repulsive, and it's also the same. The forces are the same. That doesn't mean the acceleration is going to be the same for all of these, but for all 4 cases, the forces are the same. Reason why? Newton's third law. If this pushes on this with some force, this has to push back on that with the same force. Okay? They are pushing on each other equally, even though their charges are different. Okay? All right, let's keep going. Here I'm going to get my charges multiplied are 4, and the mass of this one is 1. Here my charges multiplied are 4, but the mass of this one is 3. Okay, here charges multiplied are 4, mass 3, charges multiplied are 4, mass is 1, charges multiplied are 4, mass is 3, charges multiplied are 4, mass is 3. Okay, so what I get here are my greatest accelerations are these. Okay, A, B, C, F. All right, and then these 4 are going to be less acceleration. So D, E, G, H. Okay, now notice they are not asking us to rank the force. They're asking us to rank the acceleration. Okay, if they had asked us to rank force, totally different problem. Okay. Let's go down to this one. Students arguing about physics. Okay, here is the answer. Brian is correct. All right. Let's go to Alfredo here for a second. There's no electrical field inside a conductor. Is that true? Okay, well, depends on what he means by that. There is no electrical field inside a conductor. That's true if we're talking about the metal right here. If this is a solid sphere, the E field's 0 everywhere inside. All right? There is going to be an E field inside here, and it is going to transfer to the outside. So what's going to happen is negative charges are going to line up along the inside of this. Okay, the thing is going to become polarized, which is what Brian said. And positive charges are going to line up around the outside. Okay, the negatives are going to be attracted to the inside. Okay, and those charges are going to line up and then stay fixed. Okay, so they're not going to want to move around. That's why the E field is 0. Okay, and we'll talk about this more actually in the next video, just so you know. what's going to happen is this whole object is going to act like a point charge. Okay, so we are going to get E field lines outside that look like this. Okay, and if we go back to the beginning, this is what the net result is going to look like. Okay, and these iso lines are iso lines of potential. Okay, so let's see. It will produce a field outside the shell, yes. The total field outside will look just like the field due to a point charge at the center. Okay, that is true. All right. Okay, let's move on to the next thing. Let's take a look at a couple multiple choice questions that have to do with both Coulomb's law and FBDs. So here you see a couple diagrams. The AP people love charged stuff sitting around and charged stuff hanging around. It's like their favorite thing to do on a Saturday. And so we need to be able to draw good FBDs on this stuff and analyze what those forces are doing, their direction, okay, their magnitude, all that stuff. So here we want the magnitude of the net force on Q3, and we'll start out by doing an FBD. When we have multiple charges, here's what I like to do. I like to cover up one of the charges and analyze just the force between these two. The force between these two has nothing to do with the force that is caused and exerted on this one. Pretend it's not even there. Okay, question 1. Are these attracted or repelled? Okay, well, they are attracted. So there's going to be a force downward on this one and upward on this one. But I don't care about the downward force here. All I care about is the force on this one. Okay, and then what I'm going to do is cover up this one and look at these. These are also attracted, and there's going to be a force in this direction. Okay, now the nice thing is these are at 90-degree angles to each other. So if I calculate this force and then I calculate this force, I can use the Pythagorean theorem to find the net force. Okay, so the net force is going to be right here. All right, now I'm going to let you finish this problem the rest of the way, but I will tell you the answer. Okay, so you can check your work. And the answer to this one is 1530. Okay, so prove that, and your teacher might give you credit for finishing this the rest of the way. Okay, same thing on this one. I'll start you, and you can prove the right answer. Okay, we'll do a little bit more work together on this one. So these things are hanging, and they're repelled because of electrical force. Okay, and we have the length of the string and the angle. This is a pretty challenging problem. Let's start with the free body diagram. Okay, on this left one. So the forces that are acting, we've got mg acting downward, okay, or weight. In this direction, along the string, we have tension. Okay, and then in this direction, we have Fe. I've seen this free body diagram asked lots of times on the AP test. So make sure you understand it. This one would look very similar, except tension would be going that way, Fe would be going this way. Okay? All right, now we would like the charge. To get the charge, we have to know about Fe. Okay? To know about Fe, we have to know about these other two forces. Okay, so a couple things. First of all, we need to split tension into its components. Okay, this right here, well, let's draw both components. This right here, I'm going to put theta down here. It's equal to 6 degrees. Okay, because this, half of this is 6, and that angle would also show up right there. This is t, and it's the adjacent side, so it's t cos theta. This up here is t sine theta. Okay, now F net is 0 in this problem. So that means the horizontal and the vertical forces have to cancel out. So vertically, here's what I'm going to say. I'm going to say that mg is equal to t cos theta. All right, to this side. Horizontally, I'm going to say Fe is equal to t sine theta. Okay, now I'm going to combine these two equations. But first I'm going to set them equal to tension. So next step, I'm going to say that tension is equal to mg over cos theta. And then here I'm going to say tension is equal to Fe over sine theta. And now I can combine these two. So mg over cos theta equals Fe over sine theta. All right? Okay, now here's what I want you to do to finish it. Well, I'll do one more step with you. Let's finish this and say Fe is equal to mg sine theta over cosine theta. Okay. Now, here's how I'm going to finish the problem. I'm going to plug in all my values and get a force. I am then going to set that force that I get equal to Coulomb's law. And I'm going to solve for charge. Okay? You can just set Coulomb's law equal right here, but it gets very complicated. I would rather just solve for force and then plug it into Coulomb's law. So that's how I'm going to finish it. I'd like you to prove your answer, and your teacher might give you credit for showing the rest of the work. But the answer is 3.16 times 10 to the negative 8th. So there you go. Finish both of these problems on your own. All right, let's finish this up with a few practice problems, an FRQ, and then 2 ranking tasks. I am actually just going to give you the answers to these and let you work them on your own until you get them right. And you can check the key with me if you're one of my students, or if you are not one of my students, your teacher probably has the key available to them. Okay, so here's an FRQ. This is a parallel plate situation. We've got the field, and we're asked a bunch of questions. This is a great question. It's kind of an easy question, but it asks us pretty much about every aspect of parallel plates that we need to know about. Okay? I will give you a couple hints in certain places. All right? And I'll write down the answers like I said. Okay, so part A. Don't forget WWPCD. Okay, potential difference between the plates. Answer is 100 volts. Okay, prove it. C, determine the potential or determine the capacitance arrangement. All right, that answer is 1.3 times 10 to the negative 10th farads. Part D. Force and the direction. Okay, the force is 8.0 times 10 to the negative 16th newtons. And the direction, I'm going to let you decide that. Okay, don't forget this. Okay, that gets asked all the time. Okay, remember, it's an electron. All right, and part E. Part E is probably the most difficult part. You need to solve for the velocity. Okay, there's two ways to do this. You may do it with kinematics, which is tedious. Here's what I recommend. Solve it with conservation of energy. And the answer is 4.2 times 10 to the 6 meters per second. Okay, I think that's all you need to know on that problem. Work through it until you get the correct answers. Okay, now the last page of your packet has got 2 ranking tasks, and they won't take you very long, so do them. One is electric field, and then this is a great warm-up for the next video, because here we start talking about electric potential. This whole packet has been focused on fields and force. So our next one will be focused on potential or voltage and potential energy. Okay, so I hope you got a lot out of the videos. And I hope you have a great day. Thanks for learning some electrostatics with me here.